Be happy to. I'm Joe Lanin with Virginia Department of Forestry. I am the Virginia Urban Wood Program Coordinator, and I also help out urban and community forestry quite a bit. We're really happy to have everybody with us here today. This year, by the way, would have been the 25th annual Waynesboro Tree Healthcare Workshop, the in-person variety. The workshop was started in 1995 by Paul Revel, Dwayne Jones, and Tanya Denkla-Cobb, who are coordinating the event, and it's certainly been a wonderful series. And the first Waynesboro Tree webinar, which was held last Wednesday, September 2nd, had more than 300 people attending, and we're expecting the same amount of people today. So we really appreciate everybody who's joined us. Laura has done a great job with lining up a great speaker for today, and we look forward to hearing from him in just a little bit. As you can see, the topic for today, and also looking now at the schedule for the rest of the webinar series. September 16th, you will be Seeing Trees and the Forest with Dr. Sonia Dumpelman. September 23rd, Green Industry in the Woods and Weeds, Expanding Your Business with Woodland Health Services to New and Existing Clients. Adam and I could not come up with a longer title to that. So we decided that, we would just cut it off right there to fill up the slide. September 30th, the Urban Tree Canopy Cover, Structure and Function and Assessment with Dr. Eric Wiseman from Virginia Tech. And we certainly appreciate Doc Wiseman ending up the series for us, the 5-week series, and hopefully we'll have 300 people every week. That would be totally awesome. A little bit of future news. Trees Virginia, in cooperation with Virginia Cooperative Extension, will soon be opening registration for the Natural Area Management Webinar Series. Two guys by the name of Adam Downing and Joe Lanin are a couple of the presenters. That I think will be a 4-week series coming up later in October. And that will have a registration fee for $35. But there will be more details about that coming very soon. Also, another reminder, there's still time to register for the MAC ISA 2020 virtual annual meeting. They have lots of interesting sessions to choose from, but registration is filling up pretty quick. So be sure to check that out with the MAC ISA 2020 virtual annual meeting. Today's webinar is approved for 1 ISA, 1 SAF, and 1 VNLA CEU. You must fill out the Qualtrics questionnaire at the end of the webinar to receive credit, and it will pop up automatically at the end of the webinar. If by chance it doesn't, our wonderful Becky Woodson from the Virginia Department of Forestry and Trees Virginia will be sending out an email that will have that link to the survey, and you will be good to go once that is completed, and that's all you have to do in order to get your CEU credits. Lastly, but not leastly, as far as announcements go, you will see over in the corner a Donate to Trees Virginia button. We would be more than happy for you to send in a contribution for our scholarship program. All contributions received to Trees Virginia from the webinars go to sponsor scholarships for urban and community forestry majors. And we would certainly be glad to have you contribute, which is of course a tax deductible contribution that will be put to obviously good use. So now it's on to the exciting time. We have with us today Dr. Eric North, who is an assistant professor at the University of Nebraska-Lincoln. Eric received his PhD in urban forestry from the University of Minnesota and is currently the assistant professor of practice in regional and in the School of Natural Resources at the University of Nebraska-Lincoln, where he has developed a 4-year program for regional and community forestry. He teaches courses in green space and urban forestry management, arboriculture, tree biology, and dendrology. Eric also serves on numerous professional and community boards, including the International Society of Arboriculture and the Arboriculture Education and Research Academy. His research in urban tree biometrics, tree rings, storm and construction damage, and volunteer engagement has been published in scientific journals and industry publications. Eric is also an ISA certified arborist. Dr. North will be joining the faculty of his alma mater, the University of Minnesota, this coming January. And like Eric and I were talking before, it's a great time to move to Minnesota. Without any other ado and delay, here's Eric.
All right. Let me see if I can get this shared here.
Sure. Eric, sorry, I need to jump in here and give a little quick orientation.
Yeah. No
this is Adam Downey, folks. Thanks for joining us. Myself and Ashley Apley are kind of on the back end of things. Ashley will be fielding questions at the end. So we would like you to please use the Q&A feature of on the webinar. And I'm going to show you. So you should have something down here, something down here that looks like Q&A with the two little call out boxes. Please use that rather than the chat. We will keep track of chat, but it's easy to lose track of questions in chat. So please use this, and the question will either be answered in the Q&A feature of Zoom, or Ashley will pose that verbally to Dr. North at the end of the webinar. Okay, and so now with that, just to also have a little bit of fun here as we turn this over to Dr. North. We have good news and bad news. The bad news is that, how do I do this? Sorry, a little clunky, Adam, not good. There we go. Start with the good news, that there are more effective masks than the antiviral Norton virus, scanner thing. So hopefully you've got that, but you don't need to have it on today while we're in a Zoom meeting. The bad news is we would love to be together in person, but because of the quarantine, it is what keeps us from being together today. Eric?
All right. Thank you. Let me get my screen shared here. You can all see that, I assume?
Looks good.
All right, excellent. So if trees could talk, urban tree rings, there's maybe bonus points or bragging rights if you can identify this particular tree species here. I'll give you a hint. It's a ring porous angiosperm and is native just to the very western sliver of Virginia. So you can think about that as we go, and I'll probably talk a little bit more about that same species. So for those not familiar, dendrochronology is the science and study of tree rings through time. And it was formalized by A.E. Douglas, who really wanted to look at some interesting things using tree rings. He wanted to look at firstly, like solar cycles and how the sun cycles change. And he was able to take tree rings and analyze that and actually see some patterning there. And then he also used tree rings in what would be called dendroarchaeology, where he could take the tree ring itself and date various structures, Mesa Verde most famously, where he was able to pinpoint in time when those structures were actually built by using tree rings that were in the structure, living trees, and then, if you can believe it or not, a little piece of charcoal that they found in a fire pit, and those rings happened to overlap the dead trees that were in the structures and the living trees that were still in the area. So really quite amazing to be able to do that. And this is some other guy, I don't know, he was described on the website as a tree tourist, which, let's be honest, that's my kind of tourism. So, if you get a chance, you can go down and certainly visit some tree rings. So what else can tree rings tell us? Well, they can give us some historic information. So this was given to me by a friend of mine. These gentlemen here, there's three of them. You can see there's a guy shoveling and then two guys in a hole, right? This is proper planting technique 101. Dig the hole at least 3 to 4 feet deep, then jump in the hole with the tree after you've cut the entire top off. This happens to be American elm. And this picture was given to me by Chad Giblin of the University of Minnesota. And this building is still on the University of Minnesota. This is Coffee Hall. And this elm is still there. And he wanted to know, is the elm that I'm looking at still the same one that's in this photograph? And we were able to core the tree And we cored it at breast height, which I'm estimating off of this image is at least 7 feet off of the original root flare area. And we could find that the image was dated at 1909, and we found the tree ring for 1909 and could tell that at least this elm, the one we cored, or it was in a series of elm that were planted in that same location, were from the same area. So really cool, maybe not as cool as dating Mesa Verde, but still really cool and interesting for the folks at the university to look at when these elms were planted. We can answer some climate questions. So this is, again, this is actually a ring or a core from American elm. And if you can see it here, this is the 1980s drought. And if you have a hard time seeing the ring, this is 1 year right here. And then this is another year. And then this is a third year. So there's actually 1, 2, 3 years of growth in there. In the 1980s in the Midwest, there was a pretty significant drought. And you can see the ring afterward. This would be ring 4, and the ring before, this would be ring 0, sort of if we're looking at it this way, really changed quite significantly in terms of their tree ring width. So climate questions, and that's how we can date back and overlap tree rings, which is really quite remarkable in order to use trees as sort of these long-term gauges of climatic events. We can look at some mysterious tree damage. Here, this was just a piece of wood someone sent me and said, hey, what do you think happened to it? And, you know, I'm looking at this and I think, oh, that's kind of an interesting. You see the wound here, you see some discoloration, you see that it kept growing afterward. We see some tree rings. This is actually black walnut. Wasn't too much of a mystery. You could still see the bullet inside the tree ring. The tree had sealed over it, but what we could do is identify the year that this happened. And you can see that there's still the full metal jacket on the bullet, which is pretty cool. Not for the tree, but for us looking at it, it's pretty cool to see that. And my guess is, based on the fact that you still see these fibers here that are more torn, and that the full metal jacket's still on the bullet, that this tree was probably shot in the spring of that year, when there was more moisture and there was probably the wood was a little more supple and the bullet could enter in a little easier. So really kind of cool. My students love to see, I actually have this sample that I bring into the classroom that students can take a look at. And it's really quite interesting to see these types of samples. So let's look at some ring structure and arrangement. So this, I'm a scientist, so I love microscopic pictures, especially of wood. There's some really cool structures. We have the cambium. So that's all of this area right in here. And this is blown up many, many times. And think of it, it's only a couple of cell layers thick. And the oldest known single stem tree that's currently been verified is around 5,000 years old. So that's really an amazing thing to think about, that this thin layer of cells right here has been dividing both to the inside of the tree and to the outside of the tree for 5,000, uninterrupted for 5,000 years, which is really remarkable. To the outside, we have the phloem. That would be these bigger openings here that's transporting the sugars from the leaves, uninterrupted all the way down into the root system and through. And then this is the xylem. And just looking at this, I can tell right off the bat that this is a conifer based on how these tracheids in the xylem are arranged and what they look like. And we even see over here some resin ducts likely that this tree could use in defense. So here's what a gymnosperm looks like close up. This is an actual tree that I had cored and then sanded the top. And you can see that basically the pith would probably be somewhere back in this direction, and this direction would be where the bark would be as we're going through. And so this darker is this late wood that forms. And you'll notice that each of the vessels, these are actually tracheids, but each of these are one little dot. And I describe it to my students as looking like kernels of corn on an ear of corn. So they're packed really tight together, and that's what gives the gymnosperms some of their strength. We have ring porous. So this one, you can see the bark on this is up here. And so the pith would be down at the bottom. And this happens to be black ash. So this is 1 year of growth. So these big white here, these would be the vessels that are open. And the reason they appear white, they really should be open and you should be able to see into them. But the way these samples are prepared is I cut them with a saw and then I use increasingly finer sandpaper. So the holes fill up with a little bit of sawdust. That's why they're white. And then we have diffuse porous. And this really means, so here, here's a ring boundary here, and then the top boundary is out of the picture frame. But each of these little white dots are the vessels. This happens to be of silver maple. And so there's less organization, and you see vessels that pop throughout the growing season. All of this sort of, most of the brown material here and here are the fibers that give the angiosperms their strength, which we don't see that so much in the gymnosperms. That just gives us a little orientation of how we go about looking at these things. And Bruce Hoadley, I love books. You can see books stacked. My wife is a little irritated with how many books I have. Bruce Hoadley has a wonderful book. If you like looking at, he's got some great photos and really goes through systematically how you can identify. And he's got a couple of different books, and really a wonderful, it's all full color. So it's really cool to look through if you're interested. Vessel size, this is just remarkable to me to think of how trees move water through these vessels. So here in this image, you can see this is pencil lead from a mechanical pencil, as is this down in this corner. And that pencil lead is 0.3 millimeters in diameter, so across this way. And each of these little vessels, there's probably about 3 or 4 of them that can fit across the tip of that pencil lead. And so that's really, really quite remarkable. Here is a ring, or actually this looks like to me probably a false ring that has formed, and that structure is only about 1 or 2 vessels thick. And so this is that pencil lead, just to give you an idea of how small these structures can be. So I have looked through these many rings using a microscope essentially in order to see all of these fine features, but really cool. And then just think of that, moving potentially hundreds of gallons of water through these little tiny vessels. And it gets even more incredible. Most of the trees that we have don't use years and years and years worth of vessels. They use maybe 1 to 5 years of vessel, or 1 to 5 years of rings to actually move water. So they're moving a tremendous amount of water in these really small structures. It's really quite impressive to think about biologically. So some practical examples. I just got interested in using tree ring analysis for urban trees as I was reading through papers and thinking about how do we assess tree performance and how do we go about looking at trees. And we have lots of great systems that are used for different evaluation techniques and sometimes get used to assess how well trees are doing in a particular area. So here you see 2 gentlemen, they're measuring the tree, they're taking some diameter measurements, height measurements, they're looking at foliage, they're looking at damage and things like that to try and evaluate how well this tree is performing and maybe what value this has. Then I started reading research that said, this is a highly subjective technique. And as a scientist, I'm looking for as objective of a technique as possible. And this is not the only paper, and I didn't write this paper, so if you disagree, don't blame me. Researchers looked at different evaluators of trees using these methods, which are a little more subjective, and they found that they've got different values for each of these. So really making sure from a scientific standpoint that I was using the exact same person and technique to evaluate would have been important. But I wanted to see tree rings capture so much information. Is there a way that I could develop a tree ring system to evaluate performance of trees? So I took 2 trees here. These are both, actually, these were growing or are still growing on the University of Minnesota campus. They're both red maples, both about 10 inches in diameter. And I did measure the height, although I can't remember what it was, but they're about the same height within a couple of feet of each other. And they're only about 200 feet apart. So they're experiencing the same basic, you know, if it rains on one, it's pretty surely raining on the other, that sort of thing. And then I also took a photo of the buds. So they're bud breaking basically at the same time. I wanted to make sure, and I looked at things like twig elongation, and at least in the current couple of years, twig elongation was about the same. Buds were breaking about the same time. And there's a little bit difference in their form for some pruning, but that doesn't really tell us how well the trees are doing. It might tell us that we don't like the way one looks or we have a preference, but I wanted to know from a biology standpoint, how well are these trees actually growing? So I took out my increment borer and I cored the trees. And this is what I came up with. This gives you some idea of the difficulty of looking at maples under a microscope. They are diffuse porous, and it can be very difficult to track the different rings. So I mapped them out for you. And you can see these are both magnified at the same level, so that we're comparing like to like. And this top one here, this year 2012, is the entire distance. And here 2012 is really just right here. So quite a bit difference in growing for the same species, the same diameter, same height, same bud break and twig elongation the current year. So then here's all the rest of the years that fit into this tree on the bottom. Now you might imagine, this is a pretty obvious example, I think. The tree on the bottom represents that tree that was in the parking lot, and the tree on the top was the one that was in this little bit nicer landscaped area. What I was able to do is then go back and look at the history of these two landscapes. And what had happened in, I think it was 1996, the tree in the parking lot, that entire parking lot had been completely ripped up, and there was huge machinery, and I think there was even some Google images where you could still see the machinery moving around, and that tree was present for that. And so even years later, we see that there's a growth decline or a growth reduction, not so much decline, but a growth reduction in that parking lot tree. If I looked at the trees before, the tree rings before the year 1996, they were growing relatively the same. So they're both their rings were matching up in terms of what I would expect for what was going on in terms of moisture availability. And then I looked at how old they were, and the tree at the nicer park was 20 years old, and the tree in the parking lot was 31 years old. So that 31-year-old tree was really slowing down its growth, which maybe is a good thing in this particular instance if it's near the parking lot. Comparisons are critical, especially with some of our urban trees, and they might have quite a bit of different growing conditions or disturbances that have happened to them. And so we can't just look at the tree ring and say, oh, it's too small, or oh, it's really good. We have to compare it to other trees that are growing either where we'd like to see them grow. So we really need to compare these things in order for these tree rings to be meaningful for us. So that was the idea of what started out my thought of I should go core a lot of, I cored around 500 plus just for one or two research projects, urban trees, which hasn't been done a ton of in terms of that many. So I'll tell you, if you haven't done it before, the sample collection, you use something called an increment borer, and it's a hollow tube essentially that sticks on, and it's a threaded end. So this is that threaded, like a little screw on the end, and this is hollow on the inside. And then this is the T-bar that you basically twist it on. And then you stick in this extractor or spoon, and out comes this tree core. So this is a core from an actual tree. So it's very, very small, smaller than a number 2 pencil in thickness. So you're doing very minimal damage as you do this. Here's a picture of me actually coring it. This was mostly to prove to my wife that yes, I don't just goof around all day and talk about trees. I actually core and do some physical work on occasion. I cored it at as far down to the ground as I could get, which for urban trees and the increment bore that was appropriate was about 18 inches in diameter, or 18 inches long, so that I could core trees about 36 inches in diameter. And you only have to go about halfway through. So 18 inches was good, and 18 inches off the ground is where I cored it so I could still turn the increment bore. So just practical limitations. I will tell you that coring 500 trees on your knees is maybe a design, experimental design that I would have changed now, especially my knees are a little rougher shape. So I don't know that I would do that anymore. It's more typical to just walk up to it and core it at breast height, or that 4.5 feet. Now, the big difference there that you have to take into account is that at 4.5 feet, the number of rings that you will encounter is going to be different likely than at 1.5 feet or 18 inches. Probably not as big a deal for urban trees, which are growing a little faster in terms of their height. Bigger deal if you're using trees in a more natural area. So just something to consider where you want to core. Some trees are a little messier than others. So here is, this is elm, this is American elm, and here this little green dot is the actual pith or the center of that tree. And you can note the date of change here, and just look at that. You can see the rings are pretty symmetric as it starts out, and then you see this little bit of damage right here. And then all of a sudden we get these real elongation and really big changes in the way that that wood is developing. And then elms, I mean, if you cord it from this direction, your interpretation of the rings would be much different than if you happen to core it from this direction. You can just see these ring widths are quite a bit different. So ideally, if you've got the time and the money and the arm strength to core in multiple times per each tree, that's what you want to do. Especially when you have these trees like elms that have really, you think they're circular until you try to figure out where the center of the tree is. And then it's quite clear that they are not anywhere near circular. So just something to consider. Prepping of the cores, what I do is I mount them on this little wood block. I've made most of these wood blocks myself, the little router bit, just carve it out so the core sticks in. Now it's really important that the orientation of the core is done properly, that when you look down, you're actually looking into the vessels. If you're looking at the side of the vessel, you can't interpret those very easily. And I've seen many people mount these incorrectly and then send me samples and ask me to read them. And I say, oh, I wish I could, but you didn't mount it correctly. The other key to this is if you mount it with Elmer's white glue instead of Elmer's wood glue, if you mount it poorly, you can soak the white glue off in just some water and remount it. If you mount it with wood glue, it's not impossible, but much, much harder to get off. And so use the white glue. It allows you to make more mistakes. And then I just use a belt sander and I sand it, changing alternate directions with each grit of sandpaper as you go through, so you get a decent flat top on it. And it should look something like this at the end once you've gotten to the appropriate thickness or grit of sandpaper. So you just keep going through, and now you can see these really nice, you can see the ring boundaries and these structures going across, a little hard to see that, but those structures going across the ring boundaries, those are the parenchymal rays. So you really get a great, beautiful look at the wood and the wood grain. And it really helps you to assess these, especially if you have really tiny rings, you can see them much clearer the further down you go. Tree measurements, I use this system. There's a computerized system, but I may be a little old school. I like to look at each wood sample so that I can really identify different characteristics. And so this slide deck here that you put it on, you turn with this little crank, and then you look through it at the microscope, which you can see me doing here. I looked through 40,000 plus years of growth and measured each individual ring down to 1/1000th of a millimeter. Now I wear glasses most of the time because that's a lot of eye strain and work to look at. And then as soon as you get to the end of a ring, you push this button and then you count and you push the button, you get to a ring, push the button. So I've pushed this button more than 40,000 times. I would say closer to 50,000 times, because around the 20,000th core, you make more mistakes, it turns out. And so you end up going, oh man, and then you back it out. And so you keep pushing that button. That goes to a computer that then records the width of each thing in basically an Excel spreadsheet that then I can use to analyze the width of the core and compare those. So very cool system to use. And you really get familiar with the species that you work with by just looking at the individual grains. And you can identify years that are consistent from tree to tree. So really cool and important tool to be able to use. So I'm going to talk a little bit about how I've used these. Now, some have been in more of the scientific study that have been published papers, and I'll talk about those closer to the end. But I want to talk about a little of these case studies that I've done, which have been hired. This was a case study for a court case. It was a landscape where there were conifers growing on this landscape. One set of conifers had been treated, the other portion of the landscape had been treated with a chemical that wasn't intended for the trees, but it got into the trees and caused some damage. And then they had a perfect kind of control setup where they had a same landscape, but a different part of it that had the same conifers, roughly the same ages, and that had not been exposed to this chemical. And so the owner of the landscape was arguing with the chemical company that they basically still owed money for the damage of these trees. So in any good science, we measured the DBH so we could see, are these basically the same size? And then we measured the age so we could see, yeah, these are pretty close to the same age. So they're basically the same population of trees that we're looking at. So here's the pattern that I came up with. And in dendrochronology, it's all about patterns. And if you can look at this and discern anything useful, maybe give me a call. I looked at this and went, I have no idea what's happening. This is a lot of spaghetti. This is a lot of stuff moving all over the place. So I ended up breaking this down by decade so I could take a closer look. Now, what's happening here, these are the two trees exposed to chemicals and not. And people get excited that, oh, these two are different here and these two are different. One is way lower than the other. I'm not so much looking at, the individual year of growth. What I'm looking at is when this pattern dips, does this pattern dip? And they seem to. And when this pattern on the blue goes up, does the pattern on the red go up? And they seem to. So they're following this same general line. And so that's what I'm looking for. And since same landscape, similar things had happened in this landscape, we wanted to see, well, what happens if we take it to this next year? What do we see in terms of that? And what you can see is that this year here was the year that the chemical was applied, and then they diverge. So one goes up and the other keeps going down. And that was really unexpected because this happened to be the year that they both went down happened to be a sort of a wetter than average year. And so we would have expected both to make a nice peak in that, and they didn't. And we didn't have enough. So this is not, this is a legal case, not a scientific case. So as a scientist, I said, in fact, they asked me, are these trees ever going to recover? I said, you should call me back, in 10 years and I'll tell you, because then we can core them again, or we can look at them and reassess. We only had 3 years of post growth. So can't really use this as a scientific case, but for a legal case, it provided with other evidence that, yeah, these trees seem to be negatively impacted by this chemical that was applied to the landscape, right? So using the patterns of the tree ring as opposed to the absolute amount of growth was really a key factor in analyzing what was happening to these trees. So case study number 2, this was a homeowner that had called up a consulting arborist, and the consulting arborist then hired me to come in and assess these trees. And those of you that are arborists or work with the public, I get this a lot. People call me up and say, Dr. North, my tree just started dying this year. What happened? And I usually say, oh, you just noticed it started dying this year. It's been dying for the last 5 or 10 years is more common. So it's pretty rare that happens. So they had Norway spruce lined up along their house. They had a contractor come in and do some construction. And then that's when the homeowner noticed that the trees seemed to be declining really in 1 year. They did and then the next year the trees died. And I said, that seems unlikely, but let's take a look. And so I cored the trees because, every situation for me can be solved with tree cores. Why not? And we looked at it, and it's the pattern I found. And I thought, okay, it seems sort of this average, up and down, right? Going with sort of the seasonal averages, not a big deal. And okay. And then 2014 was the year the construction happened that the homeowner was concerned with. And then we saw 2015 just take a dip. And we did this, we cored these in 2016 during the growing season, so we didn't have that full year. And I thought, oh, that's really, I must have screwed up. I never see all the trees dip at once. That's pretty unusual. And 2014 and 2015 were good rain years. So they had nice moisture, not too much rain, there were no floodings, but really good amount of moisture. And I thought, that's really unusual to see a tree dip that much in growth. Had been a nice summer. Winters had been good, but not overly harsh. We tested for insects and pathogens and all sorts of things in the canopy and at the base. We tested the soil, no problems. And so we said to the homeowner, how did they dig it? Did they come in with a backhoe? Nope, they didn't come in with a backhoe. We made them hand dig everything. It was a fine sandy soil. We walked around, tested the soil compaction. Soil compaction was good. I said, okay, well, this is unusual. It doesn't look like there's much root damage. And clearly the trees were dead about halfway down when we just did a quick visual assessment. So I went and used Google Earth. And Google Earth allows you to magically go backward in time. And so this picture is from 2012, which was before the event. But I wanted to see, well, I expected these trees to be showing signs of decline from 2010, 2012, right, going into 2016. So we could say, nah, these trees were in decline and maybe the construction exacerbated it, but it wasn't that. 2012, I looked at that top of those, and it's not a great image, but it's the best we had. And I thought, I don't know, I don't see anything obvious there. They look green and healthy, and notice that all these crowns are connected. And 2013, yeah, they still look pretty good. Not, again, slightly different time frame. So the second picture here is in September. The early one is in April. So I was like, okay, not too bad. 2014, so this was actually, they did the construction in 2015, and so 2014, they hadn't done the construction, but I start seeing these dead branches. I think, okay, no big deal. 2014, not too big a deal, see some. And then 2015, look at that. it's pretty obvious. And where they did the construction was right here. They were putting an egress window in the basement. And we see that these canopies are completely destroyed at the top. And then 2016, it's even worse. But notice this nice line. These are not impacted here. So that kind of solidified we don't think it's a pest or pathogen. We should have seen either more random, or they should, at least the connected canopies should be showing something similar. So we went back to the homeowner and said, what else happened maybe in 2013 or 2014? And the typical, nothing. We didn't do anything, nothing happened. So even if you think it's unrelated, what else did you do? Any other improvements? Well, it turns out that same year, this is a split level house. They were fixing up the basement to live in. They installed a sump pump in the basement. Where did they drain it? They drained it right here. And then they redid the gutters in the house. Gutters on. And where did they drain it? Right here. 2014, 2015 were good rain years. They flooded these trees. The homeowner did. And by basically dumping all of that excess moisture. And when we went back and looked at it, you could kind of feel the sogginess of the ground, which we hadn't noticed too much the first time. And so I wrote my report, as I do, and I just tell anybody that hires me, I'm a scientist. The data are what the data are. And I don't think the report ever made it to the court case, but it's somewhere that people could look at and use if they wanted to. But since the homeowner had hired us, they were not as interested in what I had to say after we, kind of found a reasonable explanation. So that happens sometimes, but really kind of cool that the tree rings made us look a little deeper. So now I'm going to move on to the actual research and the influence of sidewalk replacement on urban tree growth. This was in the Twin Cities of Minneapolis and St. Paul while I was working at the University of Minnesota. So we see sidewalk and root interactions like this quite frequently. The root is diving underneath, and some engineer comes through. If there are any engineers listening, sorry, this is not going to be great for you. Nice little curve cut out. Look at that. Not a lot of room, but thanks for giving some room to the tree. In order to get that curve cut out, this is the root they cut off. This is my helmet. So you see the size of that root. And this is probably about 5 or 6 feet long, right? And just to give you context, this fence over here, this is a school, and this is where the school bus is parked to pick up the elementary school children. And now we see the tree is tilting toward that. So not great if you like children, basically, is the lesson there. So I wanted to use tree rings and see, well, okay, the tree lived, how good does it actually perform afterward? How many years to recovery? Well, so this is the graph. I'm a scientist. I make graphs, right? But let me help you out. This is basswood, had the fastest recovery. So this line right here, this line, is the line that anything over that line is recovered to previous levels of growth based on tree rings. So basswood recovered by year 2, certainly by year 3, no problems for basswood, right? Here's where we had hackberry, pretty good, kind of a junkyard dog of trees, it seems to just perform well no matter what. And so by year 4, certainly by year 5, fully recovered. Norway maple and honey locust, no recovery by 5 years. Okay, now I will tell you, our data didn't show this out. This is where it would have been good to pair it with one of the methods of tree assessment that I mentioned are a little more subjective. The Norway maple looked, for those of you that have worked with Norway maple, it didn't look good because they just don't seem to look great most of the time. And as soon as you do construction, they kind of decline even further. Honey locust, if you're surprised, it's a pretty tough tree as well. I will say, at least anecdotally, when we looked at honey locust, they looked fine. And I think what honey locust did is it said, you did some construction, okay. And it just sought a new level of growth, but they seem to look okay and be doing all right. So this is the recovery. So we basically took the years post-construction, divided it by an average of growth before the construction, so we could basically figure this out. We also wanted to look at planting space. So that in the Midwest, we call it the boulevard width, or you might call it the tree lawn, so that space between the sidewalk and the curb. And we noticed that if you have boulevards less than 4 feet, even for things like hackberry down here, if it's less than 4 feet, the hackberry didn't recover. And same thing with honey locust. Under 4 feet, the hackberry didn't recover. Once we started getting into the 6 foot, 4 to 6 foot, we started seeing recovery. And basswood, we saw recovery. And there were no basswoods in this less than 4 foot range. So that was good for the basswood. It looks like if you go over 6 feet, it starts to go down again. And this is where I would caution in terms of the interpretation. We didn't have very many boulevard widths that were above 6 feet in diameter. And so I think that's just, we didn't have a big enough sample there to really get at, but it seems like they were also improving. So bigger boulevards, if you have a small boulevard and you do construction damage, that tree is going to continue to decline and probably not recover, at least within that 5 to 7 year time frame. So growth is not the only consideration. Tilia recovered the fastest, and guess what? When we did some storm research, we found that it also fell over the best whenever you cut the roots to repair sidewalks. So Tilia was something like 2.5 times more likely to fall over. So think of it from the Tilia standpoint. If you're a basswood or a linden, you're standing there and somebody cuts your roots off and you think to yourself, I'm going to grow as big as possible in the shortest amount of time. And then the first stiff breeze that comes in, I'm going to fall over on something. And that's what they seem to do. So we had basswood really grew well, but then stability was majorly impacted. So it's not just a growth consideration. You have to consider multiple factors here in terms of what you might want to keep in the landscape. So I wanted to look also taking some tree rings and see, can I make a tree performance index that people could use to then evaluate spaces? And instead of, so this would be a very objective way to do it. So I compared DBH, which is commonly used, right? How big is the tree? And we can compare trees, and the bigger trees are better trees, generally speaking. And basal area increment, which is how we can measure not ring width, but the actual area of wood put on annually to get at growth rate. And then I developed a composite index called tree performance. And we also looked at canopy size. So how big is the crown of these trees? So DBH and performance, here's this 3D graph. So I'll just try to help you out here. This is the soil surface area. So we measured that below pervious surface area. We had the age of the tree over here, and then the diameter. So it's sort of a 3-way graph. And these are the street trees. So that gives you, and this is where the park trees were. We noticed that for the same age right here, the street trees were actually bigger in diameter than the park trees. And that was really sort of surprising. Now, the park trees tended to be older, so we had some bigger over here, but that was really surprising. I thought, well, this is a bad street trees under construction. Yeah, sure, that's great. Just do that. They grow bigger, right? So we wanted to take a look at maybe something's going on besides DBH. Canopy performance, the same basic story. Street trees, oh, that's off a little bit, but street trees here, this is the street tree. These were actually had bigger canopies than the same park trees at the same age. And like, wow, these are all very disappointing results for the narrative I would like to tell, that park trees, that we should give trees more space, essentially. And so it's kind of a head scratcher. So we're thinking about that. And I started thinking about the hydrology of urban areas. And what we do is we have houses and we tend to push water off the house as quickly as possible. And then that water that comes off the house here, we tend to push off over the boulevard. And that gets in, and maybe there's more moisture and small rain events that are getting to those trees, allowing them to grow a little bit bigger and a little bit faster. And in park trees, and parks were not irrigated parks. And so when rain comes, most of it's being captured by the canopy. And especially in a flat park, so you don't get that runoff in these sub 1 inch rainfalls, which is the average for that area. So that's a possible explanation. I'm trying to work with an urban hydrologist to see if we can test that experimentally, because it's a really cool sort of way, but it turns out it's tricky to test, but we're still working on that. So I hope to have more research coming out in the future. So let's look at this basal area increment. How did these same population of trees match up if we just looked at how much wood the tree actually put on annually? So the basal area is basically, if this is one ring, we're looking at how much physical area this is for the whole circumference of the tree, not just the width. So the width might get smaller over time, but it's expanding, and so you're ever increasing amount of area of wood. So that's a better measure for growth. And created this 10-year average and then the total to basically figure out, is the tree growing more or less? So we looked at that, and then when we do this, we see that, man, park trees really, the taller it is here, park trees really outshine street trees in terms of their ability to grow through the future and put on greater area of wood that we don't always pick up in the DBH. So really an important way to use this metric is that street trees grew really big, really fast, but then they were showing a tapering off of growth, where the park trees were like, wow, we're more slow and steady to the race, right? We're putting on more consistent, and we're continuing an upward trend of growth, which was more consistent with what we thought should be happening. So we can see that. I then created Tree Performance Index, which is a vigor index that was developed by some others. And we essentially wanted to look at the photosynthetic capacity of the crown and the stem area, so the maintenance respiration, or what the tree had to support. So we took at that, and that would give us a future photosynthetic potential of the tree. And then we combined that and did some fancy math here to basically make this ratio as a number, and we multiplied it by this BAI, which I just described, in this tree vigor index, and then took the square root, because who doesn't like square roots? It basically made the numbers smaller and easier to deal with, okay? And so this tree vigor index, we look at it, this is basically to give you an idea of how we calculated this. So I calculated the surface area of the crown of each of these trees, and then the surface area of the stem of each of these trees, so we could divide those out. And then I compared it to trees that we actually went and looked at in the landscape and said, would any reasonable person, how does TPI for this tree look? And it looked not good compared to this tree. So does this meet with a gut check of reality? If this tree over here had a higher value of TPI, I'd say that we developed something that makes zero sense. But TPI consistently showed trees that had this type of look and appearance to be what we would expect. And so it was a very consistent and clear way to measure between trees. So we did this with the extreme cases to make sure we could identify those, so that in the tighter cases, we could still feel confident about saying a higher value of TPI means it's a better tree in terms of its performance. And this is what we saw. TPI over time tended to decrease a little bit, but park trees were always above street trees for the same age. And so that was really told the story of, yeah, when we're factoring in how much photosynthetic area and the future growth potential, this is really good measure for being able to objectively analyze trees and pair that with another system. And this is basically just another way to show this. And what we really like to see here is this, man, we have these park trees that are way above the street tree performance in terms of this TPI value. Right, and so that's a really important. Now, this isn't something that the average arborist or urban forester would use. This is a scientific measure that we would try to use. Okay, and then there's future applications. So what I'm really trying to identify here is trees grow upward, and then maybe at some age they grow downward. And can we identify that? And so that's what we're looking at. So these are all the numbers on here are ages, and so that's what we're really trying to do. And it looks like we're probably going to be able to make another model to show based on boulevard size when trees decrease in growth. So we could use it as a management predictive tool. Street and park trees, just a quick note. We noticed that street trees over 50 years old they were there, but they didn't make it into any of our samples. So they're probably pretty rare. And being able to use these might give us some proactive wood utilization. Maybe we can start to identify trees before they're declined to where they might cause damage and get them out of the system, and then still use them for some other purpose that might benefit folks. So some key findings: soil surface area and age are important aspects. You can't eliminate age, and a lot of research has come out that hasn't factored in age, but that's an important part. Size and DBH, street trees were larger on average than park trees, which was a surprise. But the future growth potential as measured by the new metrics put park trees at a much higher value than street trees, which was more consistent with what we were thinking about. So metrics, we would pair it with, for those that know Bryant Scherenbrock and others out of Wisconsin, they came up with this rapid assessment. I think these TPI and BAI ratio and TPI would be good objective measures to pair with their system instead of a more subjective rating system. So kind of pairing what we've done with other folks' work and highlighting that. And then growth rates analysis applied. I get, scientists, people are like, okay, that's neat, but I can't use that. How do you really apply this? Well, I had an interesting call about Groot, And this was right before the Endgame movie was coming out. It's an Avenger superhero character. And a reporter called me and said, I hear you're an expert in tree ring analysis. Can you analyze Groot's growth rate for me between the different movies and predict his maximal height and when we should expect that? And I thought, well, there's only a few data points, but sure, why not? And so he sat with me on the phone while I modeled tree growth for Groot. And you can look it up. There's a link here. If you want to go, you can look up and read the article. I was surprised. I sent him the graphs that I made, and he's like, yeah, I'll publish those. And it did. So I will say that out of all my research, this has maybe gotten the most hits and the most reads. But if you need to calculate Groot for future movies, you now have a scientifically vetted tool that can help you out. So just keep that in mind. And with that, I'm finished. I'm happy to field questions if you want to get a hold of me. This will be my new email address at the University of Minnesota. And if you're a Twitter or Instagram person, you can certainly follow me there. And thank you very much. I'm assuming you're all still with us and listening. So with that, I'm happy to answer some questions. And I'm going to stop sharing my screen if that's okay.
Yeah, thank you a lot, Dr. North. That was great. We do have a few questions that came in.
Sure.
The first question we'll ask is, what is the effect on the tree of taking a core? So you said it's minimal damage, but they're asking how long it takes to seal that damage over.
Yeah, so these, I mean, if you can imagine what the number 2 pencil looks like, you could just barely get a number 2 pencil into one of these holes. And we are coring through the active growing tissue into heartwood most cases. So there is some damage. And there is the potential to spread disease or decay through. So we try not to core trees that are really looking unhealthy, or like maybe this tree has a lot of decay in it. So we try not to core through those areas. But I'll say I went back and reassessed a couple of things on these trees that one season later, and I could barely find on most of them, I couldn't even find the hole that I had cored in. So they had grown over pretty quickly. I had GPS points, so I knew I was at the right trees, but man, it was hard to find the actual core holes. But it does do some damage. Research has suggested that there isn't any much for long-term damage. You know, think about maple. Somebody mentioned that several people mentioned sugar maples are their favorite tree. Man, look at how long some of those sugar bushes have been tapped. And this is like that. So you get, maybe 100 years. And so damage, yes, pretty small in terms of its overall impact.
Another question we had was false rings. What is that? And how do you distinguish from a true ring?
Yeah, false rings. You can have false rings and missing rings. And a false ring, I didn't encounter them too much in the urban trees. And that's because they seem to grow a little bit faster than their more natural counterparts. But a false ring can happen. Imagine if you had, and this might happen a little bit more with changing climate and we have these more wild swings. But if you have a spring that's growing, tree is really good, a lot of moisture, tree's growing really well, and then it dries out maybe in June, and maybe it gets really dry, and maybe if it's a deciduous tree, it even drops some of its leaves. And so that ring basically seems to stop, and you get what looks like the end of the season growth. And then August happens and you get huge rainstorms and it's still enough, and the tree has plenty of moisture, and if it's the right kind of tree, it'll resume growth. So when you're looking at that, you look like what has stopped for a season, and then you look like what would be early wood or spring wood reforming. And you can tell that based on things like parenchymal rays and ring boundaries. If they're bisecting vessels, that means it's a false ring. If they're bisecting in conifers, the resin ducts, that means that's a false ring. The ring boundaries will actually go around resin ducts and around vessels if it's a true ring. And missing rings can happen if you happen to core a section. Maybe it's a really bad growing year, and since trees don't put on a perfect circle, missing rings might be it just didn't form wood over that one section where you happen to core. And so that can happen.
That's interesting. Another question we had was, did you account for discrepancies between trees that had mulch rings and trees that had grass growing directly up to the buttress roots?
Oh, that's a great question. These were all the parameters on the study where trees had to be at least 10 inches, or excuse me, 10 Yeah, 10 inches in diameter. I'm trying to think now, it was a couple of years ago when I did this. 10 inches in diameter. So they had to be well-established trees. And these are all urban street trees. And I don't know about your communities, but man, we don't have a lot of luck in the Twin Cities of having mulch rings kept around trees for that long. But I did record under each tree what was the ground cover condition. Was it mostly like sod? Was it weeds? Was it soil, rocks? And I put that in the analysis, and it just was not, it told us nothing. And which means that, at least for the trees we were looking at, there was no impact of whether or not they currently had mulch or currently had grass or currently had rocks. Now, the caveat I'll put to that is that ground cover was a one point in time measurement. So if that, if mulch in the early years had been there, we just didn't know that. And my gut would tell me that, yeah, the mulch probably helped with establishment. But if it wasn't, but in terms of if it was present when we did the cores and did the measurement, man, it just didn't seem to make any difference one way or the other.
Do you expect differences in pruning of street trees and park trees to impact the TPI value? And how would you account for that?
Yeah, good. So the way I tried to account for it in the study design was that any of the park trees had to be park trees that were maintained underneath. So they were actively mowing. So these weren't like in a natural park. These were in a maintained park area. The park trees had to be a certain distance away from hardscape infrastructure, so they weren't overly maintained. And if you look at a city the size of Minneapolis and St. Paul, they have these big roll cages on top of their lawn mowing equipment. And so those roll cages usually require an 8 to 10 foot clearance, which is also the city requirement for street trees over sidewalks. And then it's a 15 to 16 foot clearance over the street. And they use this, they happen to in Minneapolis and St. Paul use the same crews to prune the street trees as prune park trees. And so that's how we accounted for it. If you had pruning in a park tree that pruned up less, yeah, I think that would show up in the TPI because you have this ratio of higher photosynthetic area to the stem tissue alone. And so that should fall out. I mean, that should actually be incorporated into that modeling, where you wouldn't get that incorporated just in growth. You'd have to make some assumptions. And so that's how that TPI is designed to incorporate that.
And our looks like this will be our last question.
Sure.
Has your evaluations seemed to have dealt with negative inputs? Your evaluations have seemed to have dealt with negative inputs to the tree. Have you done any study on positive inputs to a tree growth?
Oh man, nobody's ever asked that before. Not for this, and I'll tell you, there's some complexities in that. And I think that's why we don't see a lot of research, especially with old trees. Now we see a lot of the research on positive inputs for new trees because funding and how long we can monitor a tree, we're really good. It's easy to plant a tree and then monitor it for 3 to 5 years. It's hard to plant a tree, look at these positive impacts and then monitor it for 50 years, or even for a street tree, maybe 20 or 30 years. It's just so hard to do that. Construction happened to be something, because they were city street trees, was recorded. And I'll tell you, the most accurate record of the construction damage for sidewalks was not the construction records. The city does the work. So we're like, oh, you must keep records of where you do work. Those were not very accurate. The most accurate was in the Twin Cities, the tax assessment of whether or not the taxes were assessed and paid by the homeowner were the most reliable form of knowing whether or not the sidewalk work was not just planned, but actually done. And then we verified it with stamps. So because of the verification nature of the negative impacts, it just turns out that that's easier to incorporate into the research. And the positive impacts are easier to do when you're talking about those newly planted trees over a shorter period of time. But yeah, I would love to. I think I'm still young enough. I could do it maybe at least 15-year study, where we could look at these positive impacts. And so I'm hoping to be able to do that.
Yeah, thank you, Dr. North. That presentation was very interesting and amazing. So I really enjoyed it.
Thank you.
Thank you.
And thanks everyone for attending.
Send us home.
All right, we want to thank everybody for joining us today. It was absolutely fantastic to have you all on board. We certainly appreciate it, and hopefully you can join us next week. Until then, we wish everyone a good week. Be safe and have fun.
Good. Thanks, everybody.
Yeah, thanks again for having me. It was great.
It's good to have you. Look forward to meeting you face to face perhaps sometime.
Yeah, that would be good.
When you get tired of that snow up in Minnesota, we'll bring you down to Virginia.
There you go.
That sounds great.